Okay, we almost made it to the end of these slides, but I have something in addition after this one. Now, one of the things, and you'll be working on this in your lab today, hard and soft water. Aqueous solubility of salts varies, and when that happens, you get hard water. Solutions of calcium, magnesium, sometimes iron and other things as well. But primarily when hard water, they're talking about calcium ions and magnesium ions. These will form insoluble compounds with soap, okay? And soap is hard to lather. That's why it's called hard water. Various removal methods for using bicarbonate and sulfate salts include ion exchange. So these are changed out for a sodium ion instead, okay? So sodium is soluble, and that's actually what causes things to appear soft and like that. It's because you've actually got a weak base that you are washing your hair with. That also allows it to have the softness of your hair as well when you work with soft water. The hard water, you essentially have a scale that you're having there. So these are ones that are soluble. So all sodium salts are soluble. Nitrates, these are all soluble. Chlorides, most are soluble, but except for silver and mercury. The sulfates are soluble except for barium, strontium, and lead. Carbonates, they are insoluble except for sodium and potassium and ammonium. And then sulfides are insoluble except for these right here that are soluble. Okay. What they don't have on here is they don't have there are certain ones, the sulfides, for example, when if you've got sulfur in your water or iron in your water, both of those are really going to smell up the water, and you're probably going to have to heavily treat that if you want to drink it or even use it for cooking. So anyway, that ends up this particular chapter. What I want to do now is I want to go on to something else. This right here is what I have. I've posted this separately as your Physical Science Test Prep 3. Next week, we will be having a test over the chapters 8, 9, 10 for this. So what I wanted to do is I wanted to go over these homework problems with you. For the most part, things seemed pretty good in your responses to these. These are the correct form for the different ones that we have for problems at the end of that chapter. Okay? And how many orbital electrons there are, and make certain you go through those and understand what exactly we're talking about each one. Because we were talking about how to recognize things from the periodic table in terms of how many electrons are there that can then form bonds, right? And the bonding then was a part of what happened in the next chapter. In that next chapter, we did not have, I do not believe, any problems, just they were all multiple choice. Make certain that you understand how the different ones are to be answered, and if there's any questions on any of those, please send me an email so that I can explain them. Finally, there's the ones that were to be turned in today, and that talks about just what type of reactions are formed, and we talked about what a strong acid would be based upon the way in which the reactions took place. We followed up on that in today's lecture by talking about that. But the key element in this particular one that some of you may have had some issues with were the problems at the end where you were doing the calculations. Many of these problems in here as well involve some calculations. So if there's any questions at all, please get back to me so that we can figure those out. the combustion yields, okay? You have to start from the balanced equation and all of that, so we'll get down below to the lower part so we can how to calculate these different ones. So for problem number 11, what you have is 0.136 kilograms of methane, and what you have is 353 grams of carbon dioxide formed. And they wanted to know how much was the yield. The first thing you have to do in any one of these is determine what's the molecular weight of each of the two species involved. And here, molecular weight here is you've got 1 carbon, 4 hydrogen, for a total weight of 6 grams per mole. Here you have CO2, so it's 1 carbon and 2 oxygens for a total of 44 grams per mole. I'm not going to calculate this again. Many of the other ones have this as the product as well. The balanced equation is CH4 plus 2 O2 forming 1 CO2 plus 2 H2O. So the coefficients here is 1 and 1. Okay? So the stoichiometric ratio, for every 1 mole of this, you have 1 mole of this formed. So how many moles do you have of reactant? How many moles do you have of product? So this right here was 136 grams, right? That's the conversion of kilograms to grams. You just move the decimal point over 3 to get it to grams. So that's 136 grams divided by 16 grams. That equals 8.50 moles of methane. For this one, you had 353 grams of carbon dioxide. That's 353 divided by 44 gives you 8.02 moles of carbon dioxide. So the actual, this is what you actually got. This is the theoretical. So the actual divided by the theoretical times 100% gives you your yield, right? That's a basic equation you do need to know. So the actual 8.02 divided by 8.50 times that 100% gives you 94.35%. We've only got 3 significant figures and everything, don't we? So we round that up, because that's a 5, to 94.4% yield. And that's why that was the correct answer there. We continue on. The next one, here we have 0.450 kilograms of C8H18. That's pentane, okay? So if you did not know what pentane was, you had ample opportunity to look up what pentane was in terms of a chemical formula of C8H18, so that you could then determine what its molecular weight was, right? 8 carbons times 12 is 96. 18 hydrogens times 1 is 18 for a total of 114 grams per mole. And this is still 44. And you're going to get 1.25 kilograms of this. Okay? So, what's the balanced equation? You have C8H18, and it turns out, in order to balance this, you have 2 moles of this for every 16 moles of this. Okay? I could have gone through all the different steps, but you should know how to balance equations by now. So you have 16 carbons here. You have 16 carbons here. You have 36 carbon hydrogens here. You have 36 hydrogens here. You have 18 oxygen there, plus another 32 there, don't you? So that's a total of 50, right? 25 times 2. Okay? So you have the same number of oxygens on both sides, same hydrogens on both sides, same number of carbons on both sides. So this gives you your coefficients in front. For every 2 of these, you have 16 of these, right? So that means your stoichiometric ratio is 2 to 16. You can make that a little simpler. It's 1 to 8, right? Both of them, you can divide both of these by 2. 2 divided by 2 is 1. 16 divided by 2 is 8. So, how many moles do you have each one of the reactants and products? You have 450 grams here, divided by 114 grams. That's 3.947 moles. Here you've got 1,250 grams divided by 44 to give you 28.4 moles. Now, remember, your ratio here is 1 to 8. So you divide this by 8, okay? So you divide that by 8 for your numerator. That's your actual. Divide by this right here in the denominator, which is your theoretical, times 100%, gives you an 89.87% yield, or 89.9%, okay? You can always back up, rewind, and go through this again if you don't understand a particular one, or shoot me a question. I'll be happy to answer it. The next one, butane combustion, and it yields this many kilograms of carbon dioxide, and the yield is 89%. Again, the first step, calculate the molecular weight. Butane is C4H10, right? That means you've got 4 carbons. 4 times 12 is 48. 10 hydrogens, that's 10, for a total molecular weight of 58 grams per mole. This is still 44. Balanced equation. For every 2 of these, you have 13 of these, 8 of these, and 10 of these. You have 8 carbon here, 8 carbon there. You've got 20 hydrogen here, you've got 20 hydrogen here. You've got 10 oxygen here, plus 16 here for 26. 13 times 2 is 26 here. So everything is balanced. Here your coefficients are 2 here and 8 here. So your stoichiometric ratio is 2 to 8. Simplifying it, it's 1 to 4, right? So here's your moles of product, right? And this is your grams per mole. So you have a total of 0.552 moles of product produced. The theoretical moles of this would be 1.38, right? So 0.138 divided by 0.89 times 58 grams per mole, which is the molecular weight of that, gives you 8.99 grams of butane. This theoretical moles, this is essentially just this right here divided by 4, right? So theoretically it would be this much, but it's only this much of a yield, so you have to divide by that 0.89, what the actual yield is, okay? And that times the molecular weight of that species gives you how many grams of butane you have initially, okay? Any questions? Don't hesitate to ask. Last one is the simplest of all, right? Here you've got this for your actual yield, this for your theoretical yield. What percent yield do you have? Actual divided by theoretical times 100% just gives you 69.6%. Very simple. So anyway, those are the different problem sets that you had to answer. And if you know how to do all of those and know the answers to the different questions, you will do extremely well on the test next Wednesday. Okay? And that test will start at the normal class time. It will only be available at that time. And you'll only have through the end of the normal class period to submit that to me. Take as long as you want to do that. And you can have one 3x5 card of equations, but just show me what ones you have, or 3x5 card of any information that you can attach then to your answers when you copy that and send it back to me. Hopefully you're getting this, and there are, if any questions though, just let me know and I'll be happy to answer them.